Welcome to 11.2. So we finally made it to series, and just an insight into how this chapter is laid out. We actually stopped talking about sequences directly for the entirety of the chapter. We focused entirely on series, but that's okay because the way that we work with series is going to rely very, very much on the techniques and the underlying math that allowed us to determine convergence or divergence of a sequence. So to illustrate what we're going to be working with and what the main ideas here are, we're going to work with a targeted example, which is actually highly visual, which is one of my favorite things about this topic. So in this, on the screen, you'll see a square that I've highlighted as having a side length of 1. Okay, so 1 unit, whatever unit you want to use. But so then the area in total here, right, available is 1 unit squared. We just want to get that out of the way so that you understand that. But we call this process halving the square. And it's actually an iterative process, just like we examined with the Cantor middle third set. So in the end, we actually end up with something which, like the middle third set that I didn't talk about very much, but we get a pattern that's what's called self-similar, which is an important property of fractal patterns. So I won't get more into that, but here's the idea. So we start with the 1 unit squared square, and then we cut that in half by drawing a line right through the middle. And there's no wrong way to cut it, right? Whether it's vertically or even diagonally, or it doesn't matter. But for the sake of illustration, and so that you see how this is a self-similar pattern, I'm going to be doing alternating cuts that are vertical and horizontal. So far what I have here is I've split up our area into halves. So the left one I'm going to label with 1/2. The right one I'm going to cut again. So I end up with now 2 squares. So if I cut, the first cut gave us 2 rectangles. Now I have 2 squares. And I'm going to label the bottom one with its area. So we know that because this is a quarter, then the area should be a quarter. And now I'm going to alternately, every one that I label, we're going to leave alone. And then the next one is going to be cut in half again, vertically. Okay, so now we have 1/8. And then we're going to cut the unlabeled rectangle again into a square and label the bottom one with its corresponding area 1/16. You can see where we're going with this. So every time we take a vertical cut, having the area, and then a horizontal cut for the remaining part, which is going to leave an area that we're going to label with 1/2 of that. And then the remaining piece, right, is going to be that self-similar part of our pattern, which is the process it looks like. Every new square that we draw in the upper right corner is going to be basically a copy of the entire pattern itself, right? So I'm going to stop labeling, but I'm just going to go ahead and continue to draw this as best as I can. At a certain point, you can't draw the pattern anymore. It's just too tiny to see. But you can be reassured, though, that regardless of how much you zoom in, right? If this wasn't a picture, if this was like some perfect fractal pattern, you'd be able to zoom in infinitely and never, ever reach the end, right? Okay, so what's the point of this? So what this picture is actually representing. Notice that every time that we start labeling the segments here, so I have the 1/2, the 1/4, the 1/8, 1/16. Each time we're getting another piece of the square labeled. And in this sense, we actually do end up labeling the entire square. That is, we get tinier and tinier contributions, but we're covering the entire square. Every distinct region, right, that's separated by these lines inside the square has a corresponding area and makes up the whole. So what we're really saying is that this picture is a visual proof of the statement 1 equals the sum, the infinite sum, from n equals 1 to infinity of 1 over 2 to the n, or written out term-wise, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32, and so on. Okay, the dots indicate that this is repeating forever. And let me highlight a few things about this notation, right? So this is on the right side, we have the term-wise expression of the series, right? But you'll recognize this buddy again. This is in summation notation. So yes, we are going to be using summation notation again. And that is representing an infinite series. Infinite because, well, it doesn't end, right? It doesn't terminate. There's no last term. So in that sense, just like a sequence, it is infinite, okay? The last thing here is this equals, it's not always going to equal something. But when it does, that's because we're saying the series converges to a real number, specifically to 1. Okay, so this is actually very celebrated and helpful result. And even though our visual proof here isn't exactly rigorous, right, it is a helpful tool for illustrating how this equation, this convergence, is true. But what do we mean by formal convergence, though? Because what exactly is that, right? So that's why we have to talk about the sequence of partial sums. So more accurately, when we talk about this infinite series, the one that we looked at, right? So when we write it in shorthand like this, what we really means is the sequence 1/2, 1/2 plus 1/4, 1/2 plus 1/4 plus 1/8, 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Okay, so this is where I mentioned before, we're going to be using the tools of sequences and that mathematical framework to really make sense of series. And that this is how, right? So what really is happening here is we can't literally compute the sum like we think of when we're talking about addition. So what we're using is we're taking the sequence of partial sums. So notice that this is S1 equals A1, S2 equals A1 plus A2. So in this case, what I'm calling A sub n, is the expression inside the summation. And so each term of this series is actually going to be the partial sum up until a certain term. So that is the sequence of partial sums is the sequence starting from k equals 1 up to n of a sub k. And one thing that's really important here is that k is a dummy variable, right? In the sense that K doesn't actually matter when we're thinking about this, right? The important thing is that we're indexing by n. So really this is a sequence in n. Okay, don't worry about the notation here. The notation actually isn't important here. What's important is that you know that when we say that this series converges, we really mean the sequence of partial sums converges. Okay, so I will summarize that as saying that this sequence converges to L, right, means so this is formally what this series equation means, right? So a series will diverge or converge depending on whether the sequence of partial sums converges or diverges. They're equivalent, exactly the same thing, right? The question is, what does the sum actually look like if it does converge? I claim that it does. So remember, we said that this series 1 over 2 to the n converges to 1. So in other words, the sequence S sub n, right, the sequence of the partial sums converges to 1. And I'm going to show that by constructing an explicit formula for the sequence of partial sums. It doesn't always exist. We can't always find it, but in this case it works out nicely. So S sub 1 is A sub 1, which is just 1/2. S sub 2 is 1/2 plus 1/4, which is, if you get a common denominator, 3/4. S sub 3 is, I'm going to take the previous one and add on the new term. That's a good way of thinking about this. You don't have to keep doing longer and longer additions. You can just use the previous one and add on another term of the series. And so this gives us 7/8. Is that right? Yeah. S sub 4, 7/8 plus 1/16 gives us 15/16. I hope you see the pattern at this point. If not, right, because it takes some intuition, I understand. So the denominators are still the powers of 2, so they're 2 to the n power. And the numerators are just off by 1. So our guess here is that S sub n, the explicit formula for it, is 2 to the n minus 1 over 2 to the n. Clever, right? So take a second to convince yourself that this must be true. And now at this point, right, we can proceed a couple of different ways. So one, even if we didn't know what this sequence converges to, we can still say that it does converge. Why? So one, notice S sub n is monotonic increasing. Is that true? Does that make sense? You're only adding positive terms, right? So it makes sense that this is monotonically increasing and bounded above. How do we know it's bounded above? Well, by sight, we'll look at the first 4 terms and say, well, it's always going to be a fraction less than 1. You can look at the explicit formula and say, well, if you can split it up into 2 to the n over 2 to the n minus 1 over 2 to the n, you'll see that it's always going to be 1 minus something positive. So it must be something that is bounded by 1. It can't be larger than 1. Or lastly, you can look at the picture that we started with, right? So it all comes back to this picture, which is we know that as we're moving through the series, right? So if we're looking at what each new term adds, right? We're adding a new segment of the square, and we can never add more than what was there in the first place, which is the square. Of course, you can't rely on your intuition all the time, but it is. And then lastly, by limit laws, the limit of the sequence, so what this partial sum converges to, right? Well, we could always use what we learned in the previous section, right? Which is that this behaves a lot like limits that we worked with in chapter 2, right? With functional limits. So think of this as some exponential over another exponential. They both have the same base. And there's really nothing here to say other than in the long run, as n gets larger and larger, these values are going to get closer and closer to each other. So this equals 1. All right, so some key insights before we move on to seeing more specific kinds of series and how to work with them and prove that they converge or diverge, right? We're going to use our intuition until it fails us, okay? And the reason why I say that is because a lot of what we deal with series is not right. By which I mean a lot of what we're used to thinking about our quantitative reasoning is limited by our experience as humans, and we are not primed to think in infinitely long things, okay? One really interesting thought experiment that you might want to, if you have the time and interest, you might want to look this up. The Hilbert Hotel thought experiment is a great way to grapple with the notion of what it means to be infinite. And the most important thing, though, is you're going to have to use the power of sequences. So everything that we built for working with sequences, we're going to apply here, okay? So in the next video, we're going to talk about geometric series, which is highly visual, and in fact, we just worked on an example of a geometric series. And then beyond that, we're gonna see some more general ideas about how to determine convergence or divergence.